Welcome to a new test and teardown video. This time it's the transmitter, receiver and filter part of the W-CDMA base station. This entire base station suffered a complete water leak and corrosion problem, so everything here is just extremely corroded and looking this bad. So I'm sorry, I need to open this and poke it apart outside because I really don't want to mess up everything here. But it is inside its shell, and that means it should be able to be mounted more or less outside in the rain. And as you can see, that completely failed. It's completely corroded. And that is, of course, because water will stay in here and, corrode everything. And that is probably why this thing was decommissioned. That will be our 48 volt input. As you can see here, we got two antenna connectors. This one is for TX and RX, and this is for RX diversity. And this is, of course, channel 3. I got the other one as well. I got channel 1 and 2. This one got only one receiver channel. That is 2 receivers and only 1 transmitter. So that is why we have a 3-bay over here. What you need to note is that we have many layers. We got the heatsink here, and then we have another layer of electronics. These two can separate, and then we have another layer of electronics. This one can go off, and then we have another layer of electronics. It's very, very compact the way that this is manufactured and designed, with all those different layers of circuit boards. Oh dear, all this corrosion. This is going to be really, really nasty. So they're using the same fan section on all their equipment, so that is quite easy. I'm just gonna attack all the screws that I can find and just poke everything to pieces here. So here in the bottom is where the power supply is located. Like that, and you can see the double rubber gaskets. They're really doing a super good job. It is nice and clean inside. Wow, great. And here's the transmitter. This is only 18 amps. So we're now again at the top side. Power supply is removed, and I've removed all the screws that I could find. And this is of course the blanking plate for the channel that is not mounted. Here is a channel. This is the RX-TX filter and 2 LNAs. I look so much forward to dig a little deeper into this unit because it consists of some really cool detail, like a motor controlled fine-tuning device. But let's just, no, we can't lift that one up. Another, ooh, that is gross. Look at the corrosion here. And this is on the outside, completely aluminium pested. Let's remove the fan section and let's dig into this. So let's try and get the filter off. But first we want to note the different connections. See the 2 coax cables in the middle? That will be the 2 outputs from the LNA section to the receiver section. And that is the output from the transmitter down there that goes to the input of the transmitter section of the filter. And of course the other channel here is not present in this unit, so they just blanked it. I took a proper tool here. It is very duck. Okay, so that was tough. So that is the lid. And look, we don't have a water leak or anything like that, so it is really nice and fine inside. By the way, all those gaskets here, they are electrically conducting, so they really went all the way to isolate completely here in this top section of the filter as well. And I can probably show you this by taking an ohmmeter. Just hold these. Look at that. It's conducting rubber. Fascinating. I think I will dig a little bit deeper into this motor tunable filter a little bit later in the video. But as you can see, this whole part can move, right? I think we're quite lucky we didn't have a leak. I mean, look at the intense corrosion and how bad all that is. Yikes. And this is inside the LNA. I will of course dig a little bit deeper into the LNA later in this video. But that was just a very first sneak peek. So now that LNA and filter section is away, I removed all the screws, so I feel that we can rotate this one and have a look. And we are of course inside. It was that easy, as you see. No cables and no nasty stuff that can go wrong. And here's that missing TX channel we don't need. And here is the transmitter. I will dig deeper into this transmitter in a later moment in the video. And here in the middle we have the receiver. So this is where the two connectors are for the receiver. And here is the data interface, gigabit optical interface. This is the transmitter section and the low level output for the transmitter. And of course the transmitter power feedback. And yeah, we got all the parts missing for the other transmitter that is not here. Let's try and pull up these boards. Oh, I touched something I shouldn't have touched. So this is the thermal design. It is of course, as always, amazing with telecom equipment how well it is thermally designed. So they do it correctly. All the hot chips, they can transfer their heat directly to metal. Look at that interconnect. How well is that done? Oh, we got a lot of FPGAs and Power PC parts and all that nasty stuff. I think this is a high precision reference crystal, that one. Yeah. And I think this is where they make the RF for the transmitter, and then it goes here. Yeah, it's done in this chip. And this is the clock reference to that chip, and then we go to the transmitter. Okay. So the receiver board, should be able to pull it up. Yes, here we go. And again, thermal. Funny they put these. They should have known that those parts are of course not present. So this is the receiver, a 2-channel receiver, by the way. We get the 2 RX channels in, and that is what this is all about. You could probably have a little fun on the name of this chip here. I don't know. Can you see what this is called? So let's look a little bit on the transmitter. Look at the different tracks here. That will be the DC power supply tracks to each of the power LDMOS. We also got an RF sense track that goes all the way around here. We got a few other tracks here. And look in the base plate how they made room for these different tracks, even different depth. See, that will be the RF track, not to interfere with the impedance. It's really well made, but you can of course understand there will be now a super lock between the revision of this board and this mechanic part here, right? You can't change any tracks at all. They are locked together, right? So let's try and look a little bit deeper into the transmitter board. Of course, this is a very, very thin, probably 0.6, 0.8, only a 2-layer Rogers or some other exotic material. It's almost white, so that reveals it to be Rogers. And you can also see in this area here, one LDMOS has been running a lot warmer. You can see there's a, I don't know if that is super visible on the video, but this one is nice and white, and this is kind of yellow orange. So I think we had a little heat up in this part here. So RF comes in here, right? And then it goes into a 90-degree coupler. So that means the phase between those two signals, they are now 90 degrees apart. And then we got a little amplifier chip here, and that's probably some bias adjustment for the amplifiers. And of course you need to have another 90-degree coupler here, and they are the classic Singer type. And then it goes into a little connector. Those connectors you see now all over the board, by the way, they are disconnect connectors. So when you plug in the part here, you will disconnect the track and you will get access to one end of that track, depending on how this one is rotated, depending if you want to measure the output here or if you want to inject something. So that is a really smart kind of test connector. Here is an isolator or a band pass filter. It is for 2140 megahertz, and that is the center frequency of the operating band for this transmitter, of course. And then we go into a power LDMOS. This is a 45 watt LDMOS. And yeah, there's not a lot of fancy smancy here. This is the gate, and that will be bias adjustment for the gate. Of course, the drain, you got DC input, and you got the RF output and the output impedance match. And then again, you got an isolator. Oh yeah, this is of course a little bit magnetic. So now I screwed up my screwdriver. And then this isolator, there's an built-in load in this one. So this both isolate, but it's also a frequency bandpass, and it matches to the input here, and all that is super smart. You can now access this track again, 90-degree coupler for the input. And here is something really, really funny about the output power stage dual LDMOS. So this is of course a dual LDMOS in one package, and the two inputs, they are coupled in parallel. As you can see here, this RF track here separates to both of them at exactly the same length and impedance and all that kind of stuff. So that means these two are just in parallel, right? And the parallel output again is just joined into this point. And then there is a different length of that track and that track. And this creates this 90-degree delay that you have on the input side because of this 90-degree coupler. So that is quite smart. And then you have a joint 50 ohm impedance. And then you go into another impedance here because you have a coupling to the output power detector. And that output detector here is the one that goes directly down to the bottom. And then there's a bottom track that goes out to this connector. Remember you saw earlier that we have an RF track here. And the reason for them putting this RF track here on the bottom, that is to create isolation. As you can understand that they don't like to have this track on the top. Also they have the different compartments in this aluminium top shield that goes down here and touches everything and super isolates all the different rooms here. But here is your power detector and another isolator with a load here. So that means if you're having a bad SVR here, it's not gonna give in signals and stuff like that in here. And yes, here's your quick connector for your filter, as I explained earlier. It's a beautiful, beautiful transmitter. I think I will save this board for decoration. It is just nice. Let's look a little bit on the receiver board. See, this one connects to this super nice interconnect. And that will be the super brain section. That will be the two RX channels. And the two RX channels, they go in here, right? And signal go to this, I think that will be down conversion. If I'm not mistaken, that will be mixers, those two little metal parts there. So of course you're doing down conversion and amplification using this Smurf IC from ST. And here is of course alias filter. So now we are down in IF and a new filter for the IF, and then data travels into those two ADS 5522 AD converters. So that will be the two parallel 12-bit 80 mega samples parallel pipelined AD converters. And all this data now goes to the data collection chip here, and it's of course doing all the fancy smancy IQ into more normal data decoding. And this board can of course also handle another RC channel in parallel, and all this data here is in this multi connector. I have not counted how many pins there is in this connector, but that is quite a lot. And then all this data now goes into the main brain card here. We got this optical interface. We got, I think this is dual port RAM that is both to the Power PC and all our fancy smancy. Those are, by the way, I think custom chips made by NEC in Japan, but they are definitely specified by Nokia in Finland because they got Finnish sounding names like this Instap, and this one here got the funny name Pimo, and that is also a Finnish name, and this one got the Heppo. And I think you should try and look at this little link. I will put a link to a little short YouTube video from Kaizer Power Electronics. He explains a little bit about the funny names on those chips. So you should definitely have a look at that video. That will make you laugh, I think. Maybe we should also try and have a look about how is this transmit signal created. And it is done in this area here. Remember, this is the input to the power amplifier. Here it's just a very low power signal, and then it goes to this Wilkinson power splitter, because they want to measure what they're sending out as well. So we got some RF switches, mixers, and all that kind of stuff here. And this is another one of these plankton, funny name. Also got a, I think this is also a mixer, right? And then that's just a DC regulator, not a lot of interest in that one. Signal coming from here, and then I believe this one is the main data creation chip, and yeah, we can't really see this on the other side, and we are mixing and amplifying the signals, and then we have of course a filter for the wanted band, and then a little amplifier here. By the way, this is this is layer 1. It's a 2 millimeter thick board, but it is 16 layers, and it is with buried vias and all the fancy smancy technology. So it cannot be a cheap board, definitely not. So we should definitely appreciate all this fantastic technology every time we call somebody on the cell phone. Let's look a little bit inside the LNA filter unit here. So this is the PCB side of it, and the other side of it, whoops, is the filter tuning section with the motor. But first we're gonna look at the circuit boards. So that will be the 2 coax cables that goes to the receiver, right? The 2 channels, they're more or less identical. They're just implemented a little bit different due to the way that the mechanics is around here, right? But what you see here is a pin that goes down to the filter, and that will connect to the internal parts of the cavity tunable filter. And I hope to reveal this later when I open this filter completely. And of course there's another pin here that connects to the other low noise amplifier, or the pre-amplifier. So here they go into a Singer 90-degree shifter, right? And then look at that, impedance match, and then the first stage amplifier. This is a tiny little chip here. It's probably some fancy smancy super low noise high gain chip, because it's all about having the highest gain at the lowest noise figure at the first stage. And then you have a second stage amplifier, and then you have a phase delay here, so that you will join the 2 signals again, right? And this looks a little bit like a Wilkinson. And then you're back to your 50 ohm system. And that's, yeah, basically all there is to say about it. Here's of course a DC connection to ground, and this length here will just make it open at the frequencies we're using. So that is more or less the 2 low noise amplifier outputs. And then we go all the way to the antenna connectors. So the fun thing is that you will have, this is of course designed to be able to do 2 things. Be mounted directly at the antennas, so you have a very short cable length to your antennas. And in that case, of course, you don't have any other tower mounted amplifiers or such located close to your antennas. Then you're using the LNAs in this unit. If you have a long cable for some reason, then you of course need to have tower mounted amplifiers, because you have loss in your cables. And that is what this is doing here. Those are called SIN, or current inductors, they isolate for the RF, but they will make it possible to feed a DC supply through the feeder to the tower mounted amplifier. And as you can imagine, the antennas and TMAs, they do take lightning strikes, and that is why we have all these big hefty components here. That's not because TMAs use a lot of power, they really don't, but it's to handle the lightning strikes to the cable and the weak coupling to the inner in the coax, because there's definitely a coupling when the lightning strikes the cable and the antenna, and that coupling can be as high as 20,000 amps on the inner conductor. So you can imagine the outer conductor current is just 100 times higher. It's just amazing currents. But these units here, they are designed to handle 20,000 amps on the inner connector, and that is because of these components here. I think that is a little bit fascinating how this is done. Oh yeah, by the way, the two antennas, one is for transmit and one is for receive only. The one that is transmitting is also used for receive. When it is doing that, it is depending on the timing. So that is the fun thing about wide CDMA band, the G3. They can either time division multiplex, so you can transmit and receive at the same frequency, or you can have different frequencies for receive and transmit, and then you can receive and transmit at the same time. So there are multiple modes depending on data rates and distances and all that kind of stuff you want to do. And of course this unit can do that, by the way. If you look at this part we have up here, this is a 4-way RF switch, and the reason why they're doing this is they have a coupler in here, because this is the TX port, and down here I am very, very sure that you will see 2 tracks for coupling to the inner conductor here in a 50 ohm feed kind of way. And this coupler got 4 ends, and all those 4 ends, they're connected here, 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 and they're of course called forward and reverse. And this way, this coupler can connect to all these different ports and measure power and reflections. And then you have the output from this RF switch goes to a detector chip, and this detector chip is the AD8362. So this is a very accurate, very wide dynamic range detector that will simply detect the levels in all the different directions and tell us what is going on with the transmitter. The digital section here is not a lot of stuff to talk about, but I think it is a little bit overpowered, over-engineered or stuff like that. So we have a huge Atmel ARM CPU with external memory. This is the program memory, and external RAM, and you got an external Ethernet controller, Ethernet transformer, and then everything here is controlled on Ethernet. Really? All we have to do is control some different gains and currents and measure some stuff. This is not doing a lot of fancy smancy stuff. I mean, really? Why is it that complicated? But this is also controlling a motor, and is also just tuning for different frequencies because of the filter is super sharp and narrow band. So depending on where it's transmitting and receiving right now, perhaps I think they will move the motor really. So I think we should definitely take out the circuit board here and have a look, and we should also look at the other end. So let's try and lift up the circuit board. That was a lot of screws, and of course I needed to solder here and pull, and solder here and pull at the same time. Look at the way that this circuit board is milled to fit the mechanics. That is just beautiful. I see a 6-layer indication here, so that is all there is to it. Did you remember what I said about the couplers? So we got actually 4 couplers here and 4 couplers here. That is a little bit cool. I was expecting to see 2 long tracks with 4 ends. But yeah, they got 2 of them. So why are they doing double forward reverse and double forward reverse? Really? That is so nice. How many VS do you think there is in this circuit board? You can even look straight through it. Oi, 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 oi. It's completely drilled through. That's yeah, that's of course the motor winding, and that will be access to the filter. And here we got access to, I believe there's a tiny little inductor here, so you can't pull these wires. Otherwise, this is a quite normal way to have it, to have a little wire wound coil going up here. It can also be on the circuit board like what they're doing here. So then it's just a stiff pin that goes into the couplers. See, this is the TX that I was talking about. In here there's the dimensions here from this to the other. Here is exactly 50 ohms. Isn't that fascinating? And then you have a double detector. I don't know why they're doing double detection, but that's just how it is. And that is of course the connector for the stepper motor. So let's go and look at the other side. And then I will go and get a screwdriver and this. So first I removed the 2 screws that holds the motor, so that means I can now simulate what this shaft is doing when this motor spins. There's probably a little gearbox or something like that in here, right? So this is what is going on. And I think I will just leave everything here, maybe just remove this screw and then remove everything here in one go and take this up so we can see what exactly is the moving parts inside this filter. Whew, that took a long time to remove all those screws. Oi, 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 oi. Look at that. So this is the technology behind this. We got some special ferrites that is moving. Wow, that is definitely some. Oh, don't you just love it? Oi, 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 what are they doing? So this that will be the TX, right? Look at that. There's a DC isolation here, and this is the DC that goes to the current inductor. And here you have a Teflon tube, and then there is a coupler in here. There's probably filling up the entire room in here with another, I don't know if we can see this, another piece of metal between the Teflon, and that will create a long cylinder capacitor, and they're very good for high power and high frequency and RF matching and all that kind of stuff. So that is the classic trick to do it like that. And by the way, we got some other really fancy things going on inside this cavity filter here. I don't know if you can see the screws here. They're nice and shiny, and those are silver plated screws, because you cannot have anything but silver and copper, stuff like that. Some special kind of materials inside this room. If you have a single screw that is a stainless steel screw in here, you're going to create intermodulation because this material is not linear when it comes to RF and multi frequencies and all that. You create a modulation, intermodulation mixed products, and that is not going to happen so much, at least when you're having more clean materials like copper and silver. So I think this is actually the only kind of metals they want to have inside this filter, just because that is how you create good intermodulation figures. And here you see a DC short, and those are of course DC shorts. I think it's funny to see that this little piece of distance you have from the ground and here, that is a complete isolation when it comes to 2 gigahertz. Oh man, so this is a quarter wave up, and then it's completely open, and then you couple to that, and then you have your output. It's just, of course, the different distance from 0 is the output impedance of that coupler, and the rest just goes via air. They couple to each other via air, and then there are the different tuning. That is the distance, this ferrite to that top part, that is the variable tuning. And if you see here, there's a tiny little screw that goes down in the hole in the middle. That is of course a mechanical tune, and this is a variable tune, and then there's a variable coupling. So this is the coupling screw and then the tuning screw between the different cavity filter resonators. And I don't know if you can imagine how long it takes to tune this and to be good enough to do this by hand. Because this is a equation with many different variable inputs. Oh, I love it. And then there's a tiny little coupling here that couples to the output screw. So the output impedance here can be tuned as well. Oy, oy, oy. Yeah, see, it goes directly over that screw. Tuning. By the way, those tuning screws, they are made so they stay exactly where they are placed. So there's a special trick with these. So they are, you can tune them, but they will stay there. They're not gonna get loose. They're quite tough to touch like this. I can't even do it with my fingers. I cannot really like this about this filter. There's a reason for the transmit to be this big, wide, and that is of course the much higher power, higher voltages, higher distances. You need everything to be, you know, much more hefty here on the transmit side. And this was the transmit port. So you see here the port goes in. Here it's different impedances, different width of the material to ground. See, this one is wide and then it goes thin for different impedance to the different couplers here, right? And that will be the RF path of this port. And this is of course the TX path to that port. Since this is only an RX, it just goes straight into the filter for the RX. So that is how this filter works. So there's only one last unit to talk about, and that is the power supply for the entire transmitter and receiver unit. And it is just another piece of beauty. Look at all those transformers. Can you imagine what kind of voltage per winding they're running this ferrite? Oh man, this is amazing. That a few windings here and then we're done. And the thermal design of this power supply is also just amazing. All the power FETs, look how well everything is screwed down. So I believe they're touching the base material here, right? This is what they're trying to do, to push them down so they will be connected. Some of them are, no, there are none. There are no FETs that goes straight through the PCB and have a direct metal to metal connection. They all transfer their heat through the circuit board to the bottom. So that is how they are doing it. I think we should try and unscrew everything here and have a look what is going on. Let's look a little bit more on the power supply. I just removed all the screws. I'm kind of impressed. Now it sticks again. Okay. Look at the thermal design here. How well that is made. So all the hot field effect transistors, they go directly down, okay, through the PCB. I kind of accept that. But ferrite, yes, that gets quite hot, so that's a direct connection to the aluminium heatsink. But of course there is a thermal resistance in a circuit board like this, but it's a multi-layer board with tons of copper in it, and you can imagine that this super good aluminium here, and it's directly connected to the back side here, that makes up for the thermal loss in the circuit board material. And this is definitely possible to high volume manufacture. Also, if you look at the DC voltage input, here is first a very, very effective filter, and then let's look at what they're doing here. I removed this as a shield that goes directly to chassis. So we got capacitors on the input, ferrite here, fuses, so 2 times 15 amp in parallel. And yes, you can actually parallel fuses, so that will give you 30 amp. Some more capacitors, and then all this filter stuff here. But look at that transistor here. So this is a field effect transistor that is connected directly across the input power. So this one goes directly to the drain, and this goes over here, right? And then we got a little diode and some stuff that is obviously connected to the reverse voltage detector. So the idea is, if somebody reverses the input voltage, then this transistor is going to short everything and blow the fuses. And this way, everything else on the circuit board is going to survive that problem. Of course, it still needs to go into service and repair, but then it's only the fuses, and then they're probably going to learn a little lesson about what not to do. But now it can be serviced. If you didn't have this reverse voltage protection, I mean, all the field effect transistors and diodes and everything that is connected to the input rail, that will just blow up sky high, right? Oh yeah, by the way, if you look at the symmetry here, so those 2 power converters here, they're exactly the same. And we need 2 very, very high powered converters to generate the 36 volts for the 2 transmitter stages. And of course, those 2 are the hottest converters on this board. And this is why they wanted to put them as far apart as possible, out at the edge, where heat can transfer to the entire chassis. Much more material, and that will make everything run colder. And they're just doing everything correct thermal design in this entire unit. So no matter what level of electronic designer you are, you can learn a million good things by looking at telecom electronics, and especially stuff in this league, because they are just doing everything to the absolute maximum top quality. So that is all I wanted to say about this fantastic transmitter. Thank you very much for watching and see you soon. Bye bye.